Hello, pre-calc scholars. This video will help us finish off our 8.4 notes on logarithms. Fourth period and fifth period ended in slightly different places, so the beginning of this video might be a little repetitive if we covered these examples in class already. Feel free to fast forward to where we finished in class. So looking at example 2 here, we are talking about evaluating logarithms. To evaluate a logarithm, we are going to think about changing the logarithm to its exponential form. So here, for example, if we're asked to find f of 32, that means we are plugging in 32 into the logarithm. So we've got log base 2 of 32, and we're trying to figure out what that's equal to. Now remember, logs find exponents. So we're going to change this to its exponential form. I'm going to think about my base first. So this is base 2 being raised to some exponent, and then that gives us 32. So I'm trying to ask myself what exponent makes 2 to that exponent equal to 32. Well, the answer is 5. And I can replace this question mark with a 5. In these types of problems, the work that you're going to show is just because, and then you're going to give the exponential statement. So log base 2 of 32 equals 5 because 2 to the 5th equals 32. So again, remember, logarithms give us exponents. Here in 2b, we've got log base 4 of 2. Log base 4 of 2, I'm going to take that 4 and use that as my base. So my work is going to say because 4 to the something equals, come back around, 2. Okay, so what is that something? 4 to what power equals 2? Well, if a number is getting smaller, it means that we are using a negative exponent or a fractional exponent, one of the two. Here, the square root of 4 would equal 2. So we want to ask ourselves what exponent is equivalent to a square root? It's 1/2. So log base 4 of 2 equals 1/2. Okay, our third example is log base 3 of 1. Log base 3 of 1 equals something. Well, our base is 3, so we start with a 3. It's raised to some unknown exponent, and then it equals 1. 3 to what power equals 1? 3 to the 0. Anything to the 0 equals 1. And that's going to be one we'll see a lot. So our answer here is 0. So again, that's one of our special properties, that log base a of 1 is always 0, no matter what your a value is. We also said that log base a of a to the x is equal to x. That this log base a essentially cancels, leaving us with x. So we'll take a little bit deeper look at that in our next set of examples, but right now you should flip to the next page and you should do these 3 check for understanding problems. If you haven't done them yet, you should pause the video and do them, and then check your answers. Okay, so let's go over the answers. Here we're evaluating f of 1 over 100. So we have log base 10 of 1 over 100. And we're trying to figure out what that's equal to. So again, start your exponential statement. This is 10 to some power equals 1 over 100. Well, if we start with a whole number and change to a fraction, that's an indication that we're using a negative exponent. So what exponent would give us 1 over 100? Negative 2. Because 10 squared is 100. So if we have 10 to the negative 2, it's telling us to do 1 over 10 squared, or 1 over 100. So our answer here is negative 2. That one's a little tricky. The first time we've looked at negative exponents with a log. Okay, so I'm going to erase this. So we said that this was all the work you would need, is just the exponential statement here. And you can just say, because 10 to the negative 2 equals 1 over 100. All right, log base 4 of 64 is going to equal 3 because 4 to the third equals 64. So our answer here is 3. Make sure it's really clear what your answer is. Our final one, a log base 36 of 6 is going to equal 1/2 because 36 to the 1/2 equals 6. Again, remember that the 1/2 is equivalent to a square root. So the square root of 36 is 6. Next up, we're going to take a deeper or longer look at properties of logarithms. We've already mentioned a couple of these, that log base a of 1 is always 0, and that's because a to the 0 equals 1. Another important one that can simplify things for us is log base a of a. So if your base is the same as what you're taking the logarithm of, the answer is going to be 1. And that's because a to the first, so take that base, loop to the 1, equals, loop back around, a. So anything raised to the first is itself. So this logarithm is going to simplify to 1. Then the inverse property, we talked briefly before that logs and exponential expressions are inverses. That means they undo each other. So if you have log base a of a to the x, the log of a is going to cancel, leaving you just with x. Similarly, if you start with base a raised to the log base a of x, this base and the logarithm are going to cancel and leave you with x, because logarithms and exponents or exponential statements are opposites and they cancel. Finally, if you're given log base a of x equals log base a of y, then we can simplify this to x equals y. We're essentially just getting rid of the logarithms, canceling them on both sides, leaving us just with x equals y. Okay, so let's use those properties to simplify some of these problems. So if we have log base 4 of 1, that is going to be equal to, well, if you've memorized the property, we know it's equal to 0. If you haven't memorized the property, then you just change to an exponential statement. So 4 to the 0 equals 1. Either way, this is how we'd show our work. Here, log base square root of 7, so let me put the base, square root of 7, equals something, raised to the something equals root 7. Well, that something has to be 1. So this is a 1. Anything to the first power is equal to itself. 5 raised to the log base 5 of 300. Well, this base and this exponent of log base 5 cancel, leaving us just with 300. So again, this one is using the inverse property that we looked at up here. Okay, now let's take a look at solving equations, not just evaluating logarithms. So here we have log base 4 of 5x equals log base 4 of 20. Well, we said we can essentially cancel the logarithm on both sides, and we're left with 5x equals 20. And divide by 5, we get x equals 4. Okay, on to the next page. The next page is about evaluating logarithms using a calculator. So you should grab your graphing calculator. You'll notice on your 83 or 84 that right below the x squared button, there's a button that says log. This log button can help us evaluate logs that are base 10. So this only works for log base 10 logarithms right now. We'll find out later how to take other logarithms on the calculator, but this button is just for log base 10. So if you have log of 10, we can actually evaluate this on our calculator or mentally. We call log base 10 the common logarithmic function. So because it's the common log, or the log that is most often used, we don't have to write that it's base 10. If you just see someone write this, log of 10, it means that it's log base 10 of 10. So if we have log base 10 of 10, we know the answer should be 1 because 10 to the first is 10. We can check this on our calculator by hitting the log button. So if you type log of 10, so use that log button, on your calculator it'll look like log parentheses and you type in 10 and hit enter, you're going to get 1. Now let's try log of 1/3. Again, this really means you're taking log base 10 of 1/3. Are we going to be able to do that one mentally? No, definitely not, which is why we need a calculator on this one. So log of 1/3, so type that in, would look like log parentheses 1/3 on your calculator. And we are going to get, let's see, approximately, and we're going to round this to 10 thousandths, that's 4 decimal places, negative 0.4771. So that's just using the log button on your calculator. Finally, let's try log of negative 2. So again, this is log base 10, base 10 of negative 2. Well, when you type that in and hit enter, you get an error. It says it's a non-real answer. That means it's imaginary. Let's think about why it's a non-real answer. So let's change this to exponential form. 10 to some exponent equals negative 2. Is there any number that as an exponent can change a positive 10 to a negative 2? The answer is no. We can't change a positive to a negative with an exponent. So we can just say this is undefined or does not exist, or no real solution. Okay, so logarithms of negative numbers, not going to work. They give us non-real solutions. Okay, so that was the common log, base 10. We also have something called the natural log. We've talked about natural base e before. E is an irrational number, and it's approximately 2.7182, but it goes on and on forever. So e to the x is called the natural exponential function, and e is a natural base. We can actually take logarithms of base e, and those are called natural logs. But I'm getting a little ahead of myself. Let's make sure we remember where e is on the calculator. If we wanted to evaluate e to the x, rounding to the 10 thousandths, with these different x values, we could say f of negative 2 equals e to the negative 2. On our calculator, the e button is right above the natural log. So in blue it says e to the x. We have to press the second button, and then the natural log, or ln, and that will give us e to the x. So on your calculator, it should look like this, either with an open box for an exponent, or with a caret like this, and you fill in the exponent. So we're going to type in e to the negative 2, or e to the negative 2. When we do that, you should get approximately, let's see, I'm going to have to erase these calculator buttons, 0.1353. Okay, now let's try f of 0.25. That gives us e to the 0.25. So you're going to hit second ln, or second natural log, and type in 0.25. And that's going to be approximately 1.2840. Finally, let's do it with a negative 0.3. So even when we type in a negative exponent, like negative 0.3, that does not give us a negative answer, right? It's just creating a smaller number here. Okay, so that's evaluating e to the x. Now let's talk about the natural logarithm. The natural logarithm is log base e of x. We shorten that to ln of x. And the reason we do that is the natural log is used a lot in applied mathematics and in science. And so it's a shortcut so that you don't have to write out the base every single time. Just like we have the shortcut for log base 10 of x, we just write log of x. Here, instead of log base e every time, we just write the natural log of x. But it's important to remember that it's base e. Okay, there is a button on your calculator for the natural log. We were just looking at it. It's the ln, so natural log. So let's evaluate the natural log of 0.3. And we're going to round to the 10,000ths. So the natural log of 0.3 is approximately negative 1.20397. That's going to push this 9 up and make this a 4, 0, if we're rounding to the 10,000ths. Okay, next, let's evaluate the natural log of negative 1. Oh, we got the same answer we got before with a common log when we tried to type in a negative number. There is no real answer or no real solution. All right, final one. Let's do the natural log of 1 plus the square root of 2. So type that into your calculator. Natural log of 1 plus square root of 2, close parentheses, is approximately 0.8814. All right, so that's evaluating the natural log using our calculator. Now let's talk about properties of natural logs. So remember, natural logs are logs and share the same properties. It's just going to look a little different because we don't see the base. So the natural log of 1 equals 0 because, remember, we're doing log base e of 1 equals 0. And we know that e to the 0 equals 1. So the natural log of 1 equals 0. On the next one, our base for this logarithm is e. So we've got e raised to the first equals, loop around, equals e. So the natural log of e equals 1, because that's the exponent that makes sense. Then the inverse property works the same way it did on the previous page, but here we don't see the base e. It's implied by the natural logarithm. So the natural log and e cancel each other out, leaving us with x. E raised to the natural log of x, the e and the natural log also cancel out, leaving us just with x. Finally, if you have the natural log of x equals the natural log of y, then x equals y. Okay, so let's use those properties to simplify. The natural log of 1 over e. Well, let's rewrite this one. We know the natural log, of 1 over e. 1 over e is the same as e raised to the negative 1. So let's evaluate that. We just said the natural log of e will cancel out, leaving you just with this. So I'm going to do that. I'm going to cancel the natural log of e, and the result is negative 1. Now, if you don't remember why the natural log and e cancel, we could also write an exponential statement. So we know that this is really a base e. The natural log is base e. Then we're looping around to negative 1, coming back. What we're coming back to is e to the negative 1. So this makes sense. It works. Negative 1 is our exponent. Okay, let me erase this so we get a little room for the next one. We've got e to the natural log of 5. Well, we said e and the natural log are inverses. They cancel. This leaves us with 5. Here, simplify the natural log of 1 divided by 3. Well, we know the natural log of 1 equals 0, and then we're dividing by 3. Let's just quickly remind ourselves why the natural log of 1 equals 0. It's because, remember this is a base e, because e to the 0 equals 1. Okay, now coming back to this, 0 divided by 3 is 0. 0 divided by anything is 0. Okay, final example. 2 times the natural log of e. Well, the natural log of e cancels. It doesn't cancel to 0, it cancels to 1. And let's remind ourselves why. The natural log of e equals, let's change it to an exponential statement. This is log base e raised to some exponent equals e. Well, that exponent has to be 1. So natural log of e equals 1. So we have 2 times 1, which is 2. Okay, so those are the rest of the notes. I'm going to assign a couple exercises on Khan Academy that you can get a head start on now that you finish the notes.